like sense. We gotta be one, work together.
Sorry.
It's okay.
I'll do
I mean,
that
that's why
next time.
Hans gave up on it, because it was just like, I'm a prima donna, you're sick of dealing with my shit. Fair enough. I'm thinking our final's gonna be take home. This is good. I knew you would.
No longer personal.
No longer personal.
Why?
Yeah.
I would much rather not do it there.
So, is this good? Yeah. So the plan will be on next Monday, because I'm anything I have to tell you, I'm going to tell you this week, and that's it. And then next Monday I will hand it out, and we will spend Monday and Wednesday in here, or whatever the hell you want to do. I'll be here to consult for 2 class periods, but there will be no new material, right? And then we'll talk about when the due date will be, but does this sound okay? And then I'll probably just have office hours during our regular finals time.
Yeah.
You can come chat, yeah, cool, yes.
Will the exam be due like the Friday of finals week?
That I don't know yet. It probably not that late, but probably Wednesday at the latest, yeah. Cause that'll be my last day on campus, cause I'm coming in on Wednesday and I'm not coming back.
I respect that.
Yeah, so it's like, it's gotta be here before my calc final.
Sweet Dr. T. You said next week we're not learning any new material, or is it the following?
Well, next week is the last week of classes, and the following week is finals.
Did you forget about that?
Yeah.
You okay with that? Yeah? Alright. Any other questions?
I live 2 weeks in one.
I don't know what that means. I don't know what's going on. Alright, is there any questions in general? If you've got your mass spring thing, I would love to collect that today. If you need till Wednesday, take till Wednesday, that's fine. I'm not gonna grade them between now and Wednesday. If you're having trouble with it and you don't know what to do, you watch my video, right? You watch it again, and then you just work along with me and we get everything happy and good. So, last thing, I guess no questions actually, right? No? There is, so let's talk about what is out and about. So there's the mass spring thing. There is a web work, right? It's Laplace transforms 1. When does that due?
Tomorrow.
Tomorrow. Do we need more time on that?
Yeah.
Can we make it on Wednesday or something?
We can. That's why I ask, absolutely. Nathan, can you send me an email that just says web work extend? Doesn't have to, you don't have to get nice and go, dear Dr. T, would you please, just the title, that's it. Just put a title on it, that was all I need. Cool, and then there will be, the final web work will be released today. And we will hopefully start on it in class if we have time. Does this all sound good?
Mm-hmm.
And that web work, Labina, do you have a question? What's the question?
Some web work like 6. Yeah. Well, the web work that's
Yes,
going on
yes.
now.
Well, let's talk.
So okay. Hold on. Okay. Number 9.
Yes.
Yeah. No, this looks really weird. Do you have it now?
Last 4 were weird.
So for number 9, I got most of it except for the last 2, and I don't know how we went.
Can I see? Oh, thank you. Oh, look at this. Man, I need an intern, by the way. You're really, like, doing some good work. So when you say the very last part, like the very last line?
The last 2. The
Oh, okay.
fraction and then the answer.
Sure. So let's make up a problem that's kind of like this. Oh shit, we'll even do cosine of 7. That's a good number we don't see a lot of. Okay. Well, I need to keep, do you mind if I keep this just a little bit so I can keep my bearings? So let's see. What in God's name do they want in the first 2 blanks? like this, so that was in the first blank,
Yeah.
Yeah.
capital Y, and then over. Did you just put L of T over, L of Y
No,
over
we just
here?
solved, like, we did the Laplace for the whole thing and
Yeah.
just kept everything where they are.
Oh, that's what they want there. Okay, got it. Okay,
With
cool.
this, I have most of it. I think I have most of it solved out besides for the part that he was talking about.
Oh, okay. This, yeah, that might help just to see what's, what is accepted. Thank you. To see what the accepted answers are, because we know web work can be picky. Cool. So those first two blanks are just take the transform. So let's do that. So I take the transform here. I have to kind of work it all the way through just to like get to where we're at. So we're gonna get minus y at 0, minus y. We're letting y be the Laplace transform of the solution. And then this is going to be 5s over s squared plus 49. And I think good to go there.
Yeah.
Cool, so yeah, so like that would be, I guess, yeah, that's the kind of thing they want in those first two blanks. And then I'm gonna give this back to you, Chris, so I don't drop it and do something terrible. Oh, I don't know about that. Okay, so this is gonna be a -2 here, so you probably need to plug that in, right? Like so. And then we solve for y, and we're gonna get y equals, this 2 will come over there. See, what's cool with the take-home is you can use the calculator, right? You can use the partial fractions calculator and make life easier. So I can give crazy things with no worries. So let's actually, I need to do this. And then this is just -2. So I gotta settle down a little bit. Divide through by the s minus 1. And then, so you're actually, am I still not to your question yet, Lavina?
No, it's right after that
Okay.
where they kind of break apart the fractions
Whoa.
and then the s minus 1 disappears.
I have no idea how to calculate.
You had no idea how to get the
yeah.
decomposition?
Because yeah.
I mean, I hope you used the calculator that I
Yes,
gave
no,
you.
I-
Yeah, okay, good,
yeah,
good,
yeah.
good, okay. Yeah, let's not get into doing that, but, I mean, I think here that they do just want you to do the partial fractions decomposition. So what's gonna happen is this one here can be written as a sum. Let's just kind of break the theory down a little bit. This would be something over s squared plus 49 plus something over s minus 1, and then we still have that dude there. And the thing with partial fractions is the number on top, or the quantity on top, has to be the most general polynomial 1 degree less than the denominator. So on top here, I would have something like this. And then over here, I just have a good old constant. And then once I find those, I would combine these two terms together because they're going to combine into a single e to the t
Oh,
thing. Does that make sense?
that makes sense.
Cool. So once you get that, and definitely use a calculator on the parfrac thing, but yeah, this will just become c minus 2 over s minus 1. Does that help?
I did use the partial fraction, but I guess my inputs were wrong because they said, well, it's not
what I
working.
kept on getting to.
And,
You kept getting an error as well?
Yeah, well, because like I didn't, and then I eventually got it, but I had to actually do it to figure it out. Like the calculator worked a little bit, but
You had to actually do
Yeah,
it.
'cause
What
like-
does that mean exactly?
like I had to look up on YouTube how to do partial fractions and actually do the math.
Oh, okay, but that's weird that the partial fractions.
Because like, okay, so what was I supposed to put in? Because I originally was putting in the 5s over the s
Yeah.
squared plus 49 times the s minus 1,
yeah.
Huh?
but it was like, it kept on.
Can you get the calculator up for me? Can somebody get that calculator up and we can check this out together? Yeah, right. Check.
Mhm.
There you go, my friend.
Thank you.
Yeah, let's see what that calculator does for this problem.
Is there a specific one or you use like any
This guy.
for the
Yeah.
the calculator?
The one that I gave a link to. It should be in
What class?
world class. look either in the announcements or content, I don't know.
I think it's at the very bottom tabs.
Okay. In the content area? Yeah, so go content all the way to the bottom. Yeah, and if somebody can, oh, you got me hooked up, thank you. You rock, awesome. So Kitra has helped us out. And so that first part is going to turn into, oh, I kind of got a feeling of what you
I
might be.
didn't put that equation
It works
in.
now.
No.
Magic.
Good. That's good. What did you say, Kitra? I'm
I
sorry.
didn't put the equation in. I think that's something that I had in there before.
Yes, this is something completely different. So let's just take a look here. Ladina, what did you fix that maybe will help Chris?
I feel like we have to use k squared for our problem.
Yeah, that's what it is. I just tried it.
That's why it
what
barks.
messes it up. Yeah.
Oh, okay. So yeah, I would. Oh, I see. Yeah, that would be. I would try like Wolfram Alpha. Try Wolfram Alpha to do that, but let's just fucking do it together. Here, hold on here. Wait, that's not how many laptops?
I was gonna take it as
Yes.
So I get to you.
So the thing you have looks like that, right? That's more of like what we've got to deal with. And then this is s squared plus k squared here, and same here. So let's just talk about how to do this. So let's say I'm going to take 5s over s squared plus k squared, s minus 1, and I'm going to break that into fractions. So this will be one of them, and this will be the other. And on top here, I want the most generic linear polynomial, and then over here I want that. Step one is to flatten this whole thing out. So multiply through by the original denominator and get rid of fractions. So when I do that, I'm going to get 5s equals, this will cancel there, and I'll be left with as plus b times s minus 1. And then when I multiply this over here, it's going to cancel the s minus 1. So I'll show you a couple things. This is good to talk about. I'm glad we're talking about it. So a couple routes to take here. The first one is, this has to be true for all s values. So I can pick good s values that give me useful information. For example, if s is 1, then this equation becomes 5 equals a plus b times 0. Yay! Plus c times 1 squared plus k squared. And now I know what c has to be, because this dies. So this is, c is going to be 5 over 1 plus k squared. Does that sound good, Chris? Yeah? Anybody else having trouble seeing what's up here? Let me know. And then, once I've got c, I still have to find a and b. So there aren't any good values that make this piece die that aren't imaginary numbers, and we don't want to go there. So what we're going to do is actually take this right side and multiply it all out. So I'm going to take, to find a and b, I'm going to say 5s equals as squared, and then the outer is minus as. The inner is bs, nice, I'm still like 5 inside my mind, and that's b minus b, and then this becomes plus cs squared plus ck squared. And I'm going to group together like terms over here. So in terms of s squareds, I've got a plus c s squared. In terms of linear stuff, in other words, s things, I've got b minus a. I think that's it. And then this is a constant, and this is a constant. And these two sides have to be equal. So the only way two polynomials can be equal is if their coefficients are identical. So that means this has to equal 0 because there's no s squared over here. This has to equal 5 because there's 5s, and this has to equal 0 because there's no constant over here. Let me stop. Does that make sense to everyone, what I'm saying, yeah? So check it out. Immediately I get B. B has to be, well, no, I don't because I don't know C yet. Let's see here. But we do know that A has to equal negative C. Oh, so I know A because I already know C. So A is going to equal negative 5 over 1 plus k squared. And then I can use this to get B. Oh, hell, right here. B and A have to equal each other, right? For this to be, wait, or equal 5. So B minus A has to equal 5. If this is A right here, then B minus that equals 5, and then, solve for B from there. Does that sound okay? Chris, does that help you? Yeah? Cool.
Yeah. So then when going about doing the inverse Laplace, it looks really complicated.
Well, it's just going to be constants that are weird, so don't
Yeah.
let those
Okay.
don't let those constants mess with you. Just pull them out in front, write them down, and then do the easier part.
Okay.
Right, because so if I was doing L inverse of this, I would break it down, actually. I would turn this into AS over S squared plus K squared plus B over S squared plus K squared, right? And then do it like this, and then this is going to be A cosine KT. This is going to be B, pull that out in front, but then times 1 over K sine of KT.
Okay.
Does that make sense? And
Yeah.
then there's some C e to the T.
Got it.
So not bad, right? After,
Yeah.
right? The constants are messy, but like the Laplace part's not bad. Other questions, friends? No? I got something really cool in store for us today. The last cool thing I'll tell you this semester, as far as I know, I need an eraser. Cool. All right. Last thing, and I kind of hope that you've all watched that video that I made on the mass spring thing, because there's an idea in that is really important to have in your head when we're doing this stuff. So we're gonna, well, let's actually get there in a minute, but let's talk about some special functions that we're gonna need. So the first one is this one, h of t. This is the Heaviside function. And in the web work you're going to get, this is also sometimes called u of t, I think. There might be something else they call it, but unit step, this stands for unit step function. Same thing. And what this is a function that is 0 when t is less than 0, and it is equal to 1 when t is greater than or equal to 0. So if we were to sketch it out, it's 0 over here. This is t. And then it jumps up to 1 the minute we get to 0. And then it stays at 1 forevermore. This is a discontinuous function. We haven't seen anything like this semester. And we're going to do a lot of cool stuff with it. We may or may not get done today with this, but it's okay. We got all week to finish this stuff up. So I want to make a little note here. Notice that h of t minus t naught shifts this whole thing. So let's actually look at what that would be. That's 0 when the argument t minus t naught is less than 0, and it's equal to 1 when the argument t minus t naught is greater than or equal to 0. Let's rewrite that. That's equal to 0 when t is less than t naught. and it's equal to 1 when t is greater than or equal to t naught. So it's the same idea, it's just it doesn't jump until time t0, t naught. So let's draw a little picture out. Oh, I need to get some gardening knee pads, that would be good. So out here's t naught, that's t. Then this function stays 0 all the way up to here. Open there, jumps up to 1 at time t naught. It's like a switch, right? So and it literally is going to be something we use to switch things off and on. Right now, it looks like it just goes on and permanently stays on. We're going to combine this Heaviside function with other things and all sorts of different ways to make piecewise defined functions. So that's kind of the first thing we need to understand in here, is how to use this to write a classic piecewise function in Heaviside notation. So let's actually title that, How to Use H to Describe a Piecewise Defined Function. And I'm just going to do a bunch of examples. I think that's really the best way. I've got some, I think, some kind of unique ways of looking at this. It's probably, nothing's unique, right? Nobody's ever done anything for the first time, but I feel like I did. I've never heard anyone else say what I'm about to say. Not that I've tried. So, let's take, for example, I've got f of t is, it is 0 when t is between 0 and 3. And then it turns on to 1 when t hits 3 and runs up to 5 that way. I'm going to do a little sketch of this too, and then it's back off when t is bigger than 5. So if we were sketching this out, let's see, so 1, 2, 3, 4, 5. That should be enough. That's t. This is f up here. So spits out 0. I don't know, I haven't really said this, but we don't use negative numbers for Laplace stuff. You probably haven't wondered, you might have wondered, but like when we're doing Laplace stuff, we're always on this domain from 0 to infinity, so we don't have to worry about negative numbers. So it's dead all the way up to 3. At 3, it jumps to 1 and stays on for 2 seconds or whatever that is, and then it drops back off. So we got a little switch. Oh, I gotta do it. This is like a little above your pay grade, this one here. Yeah, I appreciate it. So 0, 1, 2, 3, 4, 5. That's what's happening. We've got some kind of power or force or whatever you want, signal. We have a signal doing that. If you saw this drawn in normal ways, you could think of that as a square wave pulse, if you know about square waves and things like that, electronics things and signal things. So it's like a little single pulse. Boom. All right, so here's what I want to do, and I'm going to try to notate this, but luckily I think we're recording back there. I hope so. We're recording, right? Vivian, would you check that? Just, yay, thank you. Many thanks. So what I do is I work left to right, or working up with increasing t when I do this. First thing is, I look and see what is on at the start. And right now it's just 0. So this is on at the start. And what I mean by start is t equals 0. Of course you wouldn't write that because it's 0, but I'm doing this to help us notate the process. Then I'm going to use plus to turn on, so that's a plus, that's not a t, turn on, and I'm going to use minus to turn off. And I'm going to come through here and I look, the very first thing is I've got at 3. So at 3, I'm going to turn on a 1. So I put plus 1, turn on 1 at time 3. So this is turn on constant function 1 at t equals 3. So this gives me where? This gives me what that's out in front. And that keeps rolling up until 5 seconds. Now I'm going to do something a little bit different here. At 5 seconds, I want to turn that off. Actually, it doesn't get very complicated here. But I'm just going to turn off 1 at 5 seconds. So this is turn off. I don't know. Yeah, I guess parentheses are good here. Turn off the 1 at t equals 5. And we don't need to do anything else because at that point, everything's off and we've got that picture described up there. We're going to spend a little bit of time just practicing this all. And I would simplify this. This is a silly, over-notated thing, so it's just h of t minus 3 minus h of t minus 5. It's cool. It's a nice inline way to describe something that's kind of chunky up here, right? That's like a lot of real estate on the board being taken up. And that's very elegant if I understand what the Heaviside function is. Let's do another one. Let's make something a little more interesting. So let's say I've got this function. I'm going to sketch it out first. So it starts off as a sine function. And it runs up to 2 pi, just a classic sine, so that is sine of t in that realm. And then from there, it just dies off for a second. And let's see, that's like 6-ish. So let's say here's like 8 right here, nice integer. At that point, this line kicks in and I start this ramping signal. So let's see, so it goes like that, and that's going to run for 2 seconds. And it's got a height of, let's make life really easy, a height of 2, so that's a nice, right, slope 1 line, not too bad. And then it turns downward, does that, so I've got a triangle wave right there, and that's, let's say that's at 12, and then it's dead forevermore. So I want to describe that, and just assume these are lines here. We should probably know that, just to, you don't have to assume. So let's write this out in Heaviside notation. So this is f of t. So f of t equals, first thing is I start off with the sine. I don't have to turn that on. It's just the very first thing happening. I will have to turn it off at some point. So this is just cruising, and like I'm going to keep doing that until I turn it off at 2 pi. So I'm going to put here minus sine of t, and this is turn the sine off at 2 pi seconds. And what do I turn on? Nothing. There's just 0 here. So I'm not turning anything else on. Nothing else needs to be turned on. So like, if I just look at this, by the time I've reached 2 pi, I've got sine minus sine. Remember, this thing's just equal to 1 or 0, right? So it's nothing fancy. It looks fancy, but it's just saying, is this here or is it not there? Can I stop for a second? Well, I can stop. Are there any questions when I stop? Okay, nothing's happened until 8 seconds. At 8 seconds, I'm going to turn on this. I need to get the equation of that sucker. That's not too bad. Let's see, so we've got a line with points 8, 0 and 10, 2. And you probably will believe me when I say that the equation of that line is going to be, well, it's going to have a t is the slope, and when t equals 8, the output is 0, so I think this is the equation of that line right there. You could think of it as f equals t minus 8, but that's the equation of this line segment right here. Notice that when t is 10, I get 2 out. So it agrees on both those points, so it must be right. There's only one equation of a particular line that goes through 2 points. If you get 2 points on it that are right, you got the equation. So I'm going to turn on t minus 8 at 8 seconds. Cool. And then I'm going to turn it off at 10 seconds and turn on a new line. And this is the first time we've kind of seen this, where I have something to turn off and something to turn on. So you want to just go through and you just keep track. We're going to negative t minus 8. We're going to turn off t minus 8, and we haven't put the add up here yet. And I'm going to turn on the new equation, the equation of that line there. So that line, I think, has equation 12 minus t. Let's try it, let's check it out. That the equation of this one is t minus 8, but I think this is 12 minus t, and all we have to do is plug in the endpoints, and I think you'll agree with me that that works. Right? Because when t equals 10, 12 minus t is 2, and when t equals 12, 12 minus t is 0. So that's the equation of that line. I'm going to turn that on in the same breath that I turned off the previous thing. So turn that off, turn on 12 minus t. And we're going all that is going to happen at 10 seconds. So notice that, like, I'm grouping what happens at each transition together. I can read through here. It started off as a sine. The sine turned off at 2 pi. Nothing happened until time 8, at which point this turned on. 2 seconds later, that turned off, and a new function turned on. And now at 12, I've got to turn off this last one that I turned on. So we're going to turn off the 12 minus t at time 12. And then, so that's the thought process to create that descriptor for that broken-ass function. It's a pretty messy function. There's lots of sharp things, lots of, just lots of sharp things, really more than anything. Then what I'm going to do is actually simplify this as much as I can, and the only place where I could simplify is in here. This is the part where it starts to become unrecognizable. But you're going to want to do that because we're going to take the Laplace transform of that in just a little bit. So I would then simplify to make it pretty. So prettify is really prettify, is what I want to say. And so here we're going to get f of t equals sine of t minus sine of t Heaviside, t minus twice pi, plus t minus 8. Make sure to use parentheses around stuff, otherwise it'll become just hopelessly lost. When I simplify this becomes a plus 8, plus 12, so that's 20 minus 2t. So then plus 20 minus 2t, Heaviside of t minus 10. And then my final one doesn't need any extra work, then finally minus 12 minus t, Heaviside of t minus 12. That's it. I mean, that's a lot. There's a lot going on there. And especially the first time you see it, it might look a little weird. But if you think of this left to right process that I'm describing of turning off with minuses and turning on with pluses, you're gonna be in a better place. Because I mean, this looks completely alien right here, right? You might just be like, what? I have no idea. But it came from turning off something and turning on a new thing. So that part of your web work is doing this. Part of your web work is just doing this, like rewriting things in terms of the unit step function that they use instead of h. All right, let's do the Laplace transform of that sucker. So let's say I've got some function f that clicks on at time t naught. Right? I don't know what f is. It doesn't matter. I know that the picture is something like this, 0, 0, time t naught, then something. I don't know what f is, but I know it kicks on at time t naught. So, let's go to the definition. This is e to the negative st times that function. Now slow down, because now we got heavier math getting rid. I don't think we're going to finish this completely today. Don't get stressed about the web work. We'll make the due date plenty to be done. Was that even English? No. Barely. Is this making sense so far? Yeah? We're getting one. Yeah. We get to the way that you're we were doing this.
Oh, I was.
Oh, okay, I thought you were like giving me some secret. I was like, yes, that's okay. The ear wiggle. So notice that this integral is under that function. We've got e to the negative st, but then we've got this part here. The fact that this is 0 here means that it's going to kill off this entire integrand before t naught. So this integral, oh, let's write it out so you have this in your notes. This is 0 to t naught of 0 dt. Because this function is 0 on that interval. Because of that. Plus integral t naught to infinity of now this stuff. E to the negative st, just f of t, times 1 dt. The Heaviside kicked in. This is either 1 or 0. It's 1 on that interval. And now I want to do this integral. This looks very close to the Laplace transform definition, but it ain't because of that initial start time. So we're going to fix that up. And what I'm going to do is a change of variables. I want a new variable that turns this t naught into 0. So I'm going to do a shift of the whole thing. So I'm going to let u equal t minus t naught. And I'm doing that so that when t is t naught, u is 0. Let's put that up here, a little reasoning. So that u equals 0 when t equals t naught. And notice that as t goes to infinity, u goes to infinity. So the upper limit's going to remain intact. Let's see, so we got to do our change of variables. That's a constant, so the differential changes perfect. But I've got these t's in here. So like dt, this is going to become du. That's going to be 0. That's going to be infinity. I need to know what t is in terms of u. So note that. That is the word note. Note that t equals u plus t naught. So I can replace every t with that quantity. And let's do that. So this becomes integral 0 to infinity, because that lower limit went to 0, e to the negative s times t plus t naught. Just replacing that, oh, excuse me, u plus t naught, sorry. It's u plus t naught. And then this is f of u plus t naught dt. Almost done. Almost done. Let me know if there's any clarification needed there at all, friends.
So,
Hi, yeah,
in the very, very beginning,
that's okay. Here,
one more step.
one more down.
One more,
This way,
yeah,
okay,
that way.
yes.
Why is T not the upper bound? For the
Here?
0 dp, yeah.
Because, so this, if you have a piecewise function and you want to do the integral, you break it down over the pieces where things are defined. So if I'm doing an integral from 0 to infinity, what is the function's value between 0 and t naught? And because, let's actually write, maybe this will help, Kendra. So this thing here is 0, so this equals 0 when t is less than t naught. And then when t equals, or is greater than or equal to t naught, this whole thing kicks on. So it's e to the negative st f of t, when. So on the part where t is less than t naught, which would be this integral, the value, the output value is 0, right? And think of this height here, like what's the area under the function between 0 and t naught? Does that help? Yeah?
Yeah.
Okay, cool. Thanks. Other questions? Good, thumbs up, hell yeah. Right on, so this is what I got down here. Let's take that and rewrite just a little bit so that we get a nice result. So this is just integral 0 to infinity. I'm going to do a little bit of extra manipulation here. I'm breaking apart that e using the laws of exponents. That should be u, sorry. That should be u. So this is e to the negative su minus st naught, right? So I can break that exponent apart. Right, let me write that up. That's the exponent. And if you think about it, to combine these two, I would just add their exponents. And then that gets me back to where I was over there. The f of u plus t naught, I'm just going to leave. So now, this is a constant with respect to the variable of integration. Our variable of integration is u. That's just a constant, so that's going to come out in front. This is just the definition of the Laplace transform. This is the Laplace transform of whatever this is. And so I could put here t plus t naught or whatever. It's the function f with this composition first. So you're like taking the argument, adding t naught to it, then running it through f. But this is our whole function that we're applying the transform to. So I'm just writing it down here. I could rewrite this whole thing like this too, because the variable of integration is irrelevant. You can use any variable you want there. It's like a placeholder. So in the end, here's what I'm trying to say. The Laplace transform of this expression is e to the negative st naught, where the Heaviside kicked, times the Laplace transform of this function, but with a little shift first. That's the form. This is what you want. This is what we're going to practice in a minute here. That's your friend. Any questions? Okay, so let's do an example. Find the Laplace transform of f of t. Oh, let's go back to that old thing that I just did a little bit ago. So let's see, where did that little step pulse turn on at 3? That step pulse that I had earlier, did it turn on at 3 and then stay on till 5? Okay, cool. So let's take a look, let's do that. So So just a little unit pulse for 2 seconds. We want the Laplace transform of that, and I think we had a height of 1. So we described this. We said that f of t was, let's do it again. Actually, why don't you do it again without looking at your notes? Write this in Heaviside notation. And so that's 3 and that's 5. Let's practice. Ooh, I can go pee. Exciting. So glad to know.
Right back.
Knock out the Laplace transform then too. Thinking about linearity. You got that described. Good news here is the shift won't affect you because the function you're turning off and on is a constant function. So replacing t with t plus whatever isn't going to change it. And the more practice you get with this, it'll be easy. You can almost read that. Turn on 1 here, turn it off at 2. You can almost get a picture of that. Notice that the function in front is just like an implied 1. Right? There's the function in front here is a 1 in both cases. If there was a different constant there, that would be the function. And that would be your final answer. Yes?
Would it be 3s and 5s?
Did I?
Because on there's like e to the s negative s t naught.
Yes, and T naught here is 3.
Oh right, because it's not a plus. Oh, sorry.
Does that make sense? Is it okay?
Yeah.
It's cool. I appreciate you checking on it though. Means you're thinking about it, so that's cool. So a thing to keep in mind is when you see an E to something S, that means a Heaviside happened or a step has happened. Something discontinuous has happened when you see an E to something S. It's got an S up here. That's the only way to get it is through discontinuity or just this Heaviside flipping off and on. Let's try one more. Let me know if there's any questions on that, but I want to do just a nice simple one. So let me give you one to try. So let's say my function goes 1, 2, let's be real, oh, so chill. Oh no, let's do t squared, that'll make it more fun. T squared. So starts off as t squared, turns off, dies the rest of the time. Let's first write that in Heaviside notation. And then we'll do the transform together, unless you just feel like, rocking it out yourself. You should. T squared gets turned off at t equals 2. Once this is in full effect, it's t squared minus t squared forevermore. And let's make sure, don't let me move forward if you don't understand what's going on there. Because the rest of this is just going to be mumbo jumbo. Go forth and find the Laplace transform, if you dare. I'll start giving some hints in just a minute or two. Give it a shot. I'm gonna come around here. Folks want to tell me, is this working for you? Is this making sense? Well, it's not, so it's t squared, so we start off with t squared, right? Working left to right. T squared, so like if I didn't have that Heaviside thing in there, it would just be a parabola. F of t is t squared forevermore.
That's t squared, that's.
Well, that would help.
Yeah.
Yeah, there you go. I'm glad we had this chat. Thank you. You're welcome. Is this working for you? So inside the Heaviside, you'll never have anything except t minus a time where things turn off and on. It'll always, none of the functions ever go inside there. You just multiply this by the thing you want to turn off or on,
Okay,
on the outside.
so we're multiplying what?
Mm-hmm.
And that's where we're starting out.
Yeah, exactly. So without this, if I didn't have this, this would just be a parabola forever. But as soon as t hits 2 or more, that turns into a 1, and I've got t squared minus t squared for the rest of time. 0, they cancel each other. Does that make sense? Yes. Excellent. How's it going? You got anything you want clarification with? Oh, you're already like moving forward. Beautiful.
Well, I think this is right, because I split it up. I am confused because we haven't done one of these yet where it's like t squared times the Heaviside.
We have, that's the function that, we haven't done the example. Yeah, it's kind of, we haven't actually done
Oh, we didn't take the Laplace.
We haven't done that yet, yeah, so it's, do you mind, is it okay if I write on here?
Yeah, of course.
Okay, I want to write this up here so you have it for yourself. Just so you have that right in front of you, that's the thing we're going for. Okay, cool, okay.
I guess I'm confused about what I'm supposed to do with it.
Okay, so, well, let me get up there and let me give a little guidance, and this will help. So the next step. Got one more. So what I'm going to do this one we got, right? This is just 2 over s cubed. That shouldn't be shocking to you at all. 2 factorial over s cubed. But now this one, I'm going to pull the Heaviside out in front and be done with it. So the minute I do this, I'm done with the Heaviside. So just bring it out in front as that. And then this t squared, I'm going to replace t with t plus 2 quantity squared. So let's put the law back up again so we can see it and compare in case that's confusing. The rule I'm using is this: Laplace of f of t, h of t minus t naught is e to the negative s t naught, Laplace of f with t replaced by t plus t naught. So you've got to do that sub. You've got to sub every instance of the variable t with t plus whatever the time is. And then simplify. So that's like, Hans, does that help like kind of see where to go with that? Any questions on getting to that point? You good, Vivian? You're still thinking about it, pondering? Yes. So I'm not done. I'm going to now expand that out because I don't know how to do that Laplace transform, but I sure know how to do all of these. So this becomes now it's just like classic Laplace transform. In a lot of ways, you know, the notation helps you. I don't have to think about Heaviside anymore. I've done the thinking by putting that out in front. It's a little note to self that this is a Heaviside thing. So then this just becomes 2 over s cubed plus 4 over s squared plus 4 over s. And I'm done. That's the transform. Vivian, yes ma'am?
Why is that t plus 2 squared?
Because to do this transform here, Laplace of f of t times a Heaviside, I bring the Heaviside out in front like this, and I replace the t in the function with t plus t naught. So here t naught was 2, so I'm replacing every t with t plus 2.
Oh, okay.
Yeah? Yeah? Cool. More questions? It's like once you get this rhythm, you'll rock it. It's just like practice. But this is the answer you want to be coming up with. Okay, let's talk about the inverse transform. So, L inverse of e to the negative st naught. The minute you see that, e with a negative s on it, that's like Heaviside. That clues you off. This is a Heaviside thing. That cannot occur. There's one other way it can occur, but it's like a jump function. So L inverse of this is equal to Heaviside. So now this comes out as a Heaviside, t minus t naught. L inverse of whatever this thing is. And after I'm done, I'm going to replace t with t minus t naught to go backwards. It's just that rule completely backwards. So like, right, putting on the socks and then the shoes. And the way you want to do that is you take the shoes off first and then the socks. So I'm just doing the order of operations in complete reverse. So let me do that. Let's do this one, undo it, and let's see how it turns out. So let's do that. So what is L inverse of 2 over s cubed minus e to the negative 2s, 2 over s cubed, 4 over s squared, 4 over s. There's nothing special about this. It's just good old Laplace stuff, because there's no e to the negative whatever. So this just becomes 2t, or t squared, excuse me, t squared. That shouldn't be surprising, because literally what we said, right? We know what the answer is here. We just got to see it. And we're not going to see it for a little bit, so that's why I want to do this. So then minus, now this dude comes out as the Heaviside, t minus 2. And this will always be t minus something. You're never going to have t plus something, because we don't have negative time. Okay, right? Just always t minus. We could, but you know. But we're not going to. Times L inverse of this shit, to use a technical term. Sorry to get all technical on you. And then after I do that, I'm going to replace every t with t minus 2 after I do the transform. So this is equal to, I guess I better move up. So equals t squared minus Heaviside t minus 2. That's just t squared. That is just 4t. That is just 4. And I'm going to replace t with t minus 2. Now it doesn't look like what we started with, right? It looks very different. Remember what we started with? T squared minus this times t squared. That's what we started with. But when we do this sub, this is all going to change. So this is t squared minus Heaviside, t minus 2. Now I'm going to replace every t with t minus 2. And then simplify with like the suspense, right? I need a little drum roll for sure. Minus Heaviside, t minus 2. Foil that sucker. We're back. We're back home. That's a long trip. But it's a fun trip. I love this stuff. I don't know if it shows. Probably a little bit. Just everything we do in here is just like always pure joy. For me. For me. I want to show you one more thing. We'll come back on Wednesday. So the web work probably is open.
Mm-hmm.
Feel free to get in there if you don't have anything else to do. But get other shit done first. because we're gonna come back on Wednesday. I'm gonna show you how to put this all together, and then we'll start working on that web work together. And hopefully knock out most of it. But I want to show you one last thing. The Dirac delta. Very exciting. So this is the weirdest fucking function you'll ever see. It's not a function. We're going to pretend it is, but it's not a function. It's a thing called a distribution. It's a distribution, not a function. Because we cannot write out a definition for it. I can't say the Dirac delta of t equals this. There's no definition I can write out here. But this here is the Dirac delta. And we can think of it like this. So this is not right, but it's a good way to think of it. It's equal to 0 if t is not 0. And it's equal to infinity if t equals 0. And the shifted version, which puts an infinity at time t naught, looks like this. It's equal to 0 if t isn't equal to t naught, and it's equal to infinity if t equals t naught. So it's a function that looks like this. Dad, everything, right there. Yeah, Chris.
Is this like my own personal pleasure question? Is this something to do with the Dirac equation?
Maybe.
The wave equation?
Yes.
Okay.
Yeah.
Cool.
100%. Yeah. Here's another way to think of it. So that's like the cheesy way to think of it. But here's the way that it really will matter to us. It's best understood in terms of being inside an integral. So if I have an integral from a to b, and I have a function, you've got a problem in your web work like this, times Dirac delta of t minus t naught, and let's say that that t naught is in this interval from a to b. Hell, it could even be on the ends, I guess. So t naught is just somewhere inside that integral. So let's see, here's a to b. Here's my function, f of t. And the Dirac delta is acting at this point t naught here. That integral is just equal to the value of this function at t naught. So it just grabs a single point. The whole integral turns into the value of f at t naught. All the weight is put on that t naught. Everything else is dead. It's a very strange thing. It's very strange. And like trying to reason this out, there's ways to get at it. We don't have time, but we could get at this. And if you're interested, I'll happily send you some material so you can understand the Dirac delta a little bit better. But let's really quick knock out one thing here. What is the Laplace transform of a function times a Dirac delta? And we'll end it here. So we'll just get this and we'll pick up. You go to the definition. Bless you. It simply ignores everything except what is happening at t naught and samples this function at t equals t naught. So the answer is just this, e to the negative s t naught, f of t naught, and that's just a constant. But the fact that this is in there tells me that a Heaviside is nearby. This is the indicator for Heavisides. Heaviside was now introduced somehow, and we'll see on Wednesday how to undo it all. So isn't it nice that it'll be a take-home final? Yeah, I think so too. You can do it on the beach. If you're on a beach, if you're near a beach. do I have, if anyone wants to get me their mass, spring thing, I'll take it now. If not, Wednesday's a great day to